In our previous lessons, we were talking about ways to calculate the average rate of change, or the slope, for our equations. So we always said we can use 2 points to find the change in y over the change in x. And we talked about finding that graphically, algebraically, and also tabularly. So again, we use 2 points as a reference, and we're looking at the rise over run, the change in y over the change in x. So let's take a look at a couple of examples. So here we want to graph y equals 5x minus 7. And so what we were doing before is we made a table of values, and we substitute values in for x to figure out what outputs came with that. So for example, if we put 0 in, we've got 5 times 0, that's 0. 0 minus 7, that would be negative 7. 1, input that in. 5 times 1, that's 5. 5 minus 7 is negative 2, and so on, and we started plotting the points accordingly. Now we also noticed that when we had our table, we looked at the change of the outputs, the change in the inputs, and notice the change between the 2 points was adding 5 for every 1 changed the x. So our rate of change, our slope, was 5 over 1. Notice how that appears in your equation. Right here, that's representing your slope. So we know that from point to point on our graph, we're going to have to go up 5 units and to the right 1 unit to get to the next point. And we also know here, when we start with 0, right, we put that into our function, we got out negative 7. Well, 0, negative 7, that represents the y-intercept for your graph. So we can use that as our starting point to plot more points for our graph. And again, starting here at your y-intercept, we're going up 5 to the right 1, we put a point, up 5 again, to the right 1, put a point, all the way through, extending until we run out of space on our graph. And so that at this point, we know those were just some sample input for the outputs. We can have an unlimited number of inputs to get the outputs, so this would have to be a continuous relationship. Since it's continuous, we would have to connect the points. Now, does this graph represent a function? Remember, our definition of function means for every input you have one output. So, as we check, every input has one output, we have a function as well. Now, just like we did before, we want to talk about the domain and range and any x-intercepts that exist. So the domain is a set of all of the input values for our function. So we look and to see, do we have any limitations to what values we could put in the x values for our function? And we can see with our line, it would continue in each direction. That means we're using all these inputs to the right and all of them to the left. So we know our domain has no restrictions, so we could say it's from negative infinity to positive infinity, and that would be inside your parentheses. The range, we're looking at the output. So vertically, we're going to check and say, is every output being used on your function? And it is. There's no restrictions. So our range would also be the same as our domain, saying that your outputs are going from negative infinity to positive infinity. The next question is, do we have any x-intercepts? Remember, x-intercepts are places where it crosses the x-axis, and when that happens, it means the output is 0. And we can see on our graph that it's happening here. We just don't know exactly where because there's no grid point. Well, never to fear, we still have a way to solve. Since the output is 0, that means we can go to our function, and here where our output is, we could put a 0 in its place. So we're going to think about 0 equals 5x minus 7. We can take this equation and undo it to solve for x, and that would be the coordinate needed to finish our x-intercept. So to undo this, we would add 7 to each side and then divide by 5. So the x-coordinate would be 7/5. Therefore, our x-intercept, which is happening right here, where we can visually see it on the graph, is at the location 7/5, 0. So to review, When we were working with graphing our linear function, a couple things stood out. We had a starting point, and remember that starting point occurred when you had an input of 0. And so when we put in 0, what did we get out? -7. Notice where that shows up on your equation. Your starting point is here on your equation. Then we knew to travel from point to point on our graph, going up 1 and to the right 5 was our pattern that we saw in the table. And we said that's right here in the equation. That's your rate of change, your slope. So if we start noticing these items within our equation, we no longer have to create a table of values to find the points to plot. We can just use those as our guide and go from there. So let's take a look at another example. Here we want to graph y equals -2/3 x plus 1. So a couple things to look for. We wanted to have a starting point, and then we need to know the rate of change. So what do you think would be the starting point of the graph? What coordinates would you use? Well, what I'm going to do is look at my equation and see where that starting point is. And remember, we said that happened here. So it's saying that we started at 1, and that was when the output was that value. So that's giving you the starting point, the y-intercept of 0, 1. So if we had our scale of 1s on the graph, we could plot that point, and we have it at 0, 1. The next thing we know is the rate of change. And again, that came from this point on our, I shouldn't say this point, this location in our equation, and that's telling us how we move. And so remember, it's the change in y over the change in x. So this change is negative. That means we're going down 2 units and to the right 3 units. So at that starting point, 0, 1, the y-intercept, we travel down 2 units to the right 3 units. This would be the next point on our line. And we repeat again, down 2 to the right 3, there's our next point. Down 2 to the right 3, there's our next point. And we do that all the way through our graph. Now, once we run out of points to go this way, we could then do the inverse and find more points in the other direction of the graph. So instead of going down 2, we can backtrack and go up 2 and to the left 3 and generate more points on our line. Now, we were just using our starting point as an example. We know that we could pick any value for x and substitute it into the equation and get an output for y. Therefore, this would be a continuous relationship, and we would connect it with a line. So does this represent a function? Yes, it does. Every input has one output. What can we write as its domain? So again, you're looking to see the set of all the input values are being used. And we know there is no limitations on that, so we know the domain would go -infinity to +infinity. The range would be next. Any restrictions on the outputs that you can use? Again, no restrictions. We'll have an output that goes with every input, so we're going to use -infinity and +infinity again. The next question is, do you have any x-intercepts? Any locations where your graph crosses the x-axis? And we do. We can see it on our graph. We just need to know the location. So again, it's not at a grid point. We know x-intercepts have an output of 0. So if we put 0 as the output to our equation and solve, we'll know the input that goes with it. So to undo this equation for x, we would have to add 1 to each side of the equation. Then, then we would have to undo the division of 3 by multiplying by 3. So we now have -3 equals -2x. Then we'd have to undo the multiplication of -2 by dividing by 2. So a negative divided by a negative would be a positive. Therefore, we'd have 3 halves as our value for x. So now we have the coordinates needed for our x-intercept. So we know that the x-intercept is at 3 halves 0, and again, we can see that visually here on our graph, and we've proven it algebraically. Here's our next equation. We want to graph y equals 3. So again, you're going to ask yourself, where's the starting point for your equation. And again, it was the constant value. And here we say y equals 3. Well, we know where 3 would be on our graph with a y value of it, so we could plot that point. And notice how that's your y-intercept. Now, is that the only place where y equals 3? No, it's not. We know y equals 3 here, and here, and here, y equals 3 here, and here, and here, and there's no limit as to where y equals 3. It would continually happen, right? And we can see how it's forming a horizontal line. So what does that mean about the rate of change? Well, you're not going up or down at all. You are staying consistent. That means the rate of change is 0. Notice how in your equation you do not have a number and an x involved. You just had the output of 3. And that's what the graph is showing you, where all the outputs of 3 are. Would this be considered a function? Yes, it would. What would be the domain? Well, as we look at the inputs, there's no restrictions, so that would go from negative infinity to positive infinity. What about the range? Well, for outputs, every single output is 3, and so that's very specific. So we would just say 3 is the range, and that's within our brackets. Do we have any x-intercepts? Any places where it crosses the x-axis? No, we do not. And so we don't have any x-intercepts, so we would just write none. All right, how about this one? Let's graph x equals 3. So what do we know from this equation? It's saying x, your inputs, have to be 3. Well, where would that show up on your graph? Well, we know x is 3 here, so that could be a location. It also would be 3 here, and here, and here, and here, and we have an infinite number of places where the input is 3. And notice how that's forming a vertical line. So here we have a continuous relationship where the input is 3. And we know the coordinate of the x-intercept, 3, 0. Would this be considered a function? No, it would not, because for this one input of 3, we have an infinite number of outputs, therefore it would not be a function. What would be the domain? Well, the domain is all the inputs being used, and here only one input is being used, and that's 3. So here we would have 3 within brackets for the domain. What about the range? Well, the set of outputs. As we look, there's no restrictions on the output, so that would be from negative infinity to positive infinity. Do we have any y-intercepts? Any places where the graph crosses the y-axis? No, we do not. So we have no y-intercepts for this relation. So here we have the equation y plus 1 equals negative 4 times the quantity x minus 2. And you can see that this is written differently than the other equations. We could take this equation and simplify it so it matches the other formats. In order to do that, we would multiply negative 4 through to x minus 2, which means we would have negative 4x plus 8 is equal to y plus 1. Then we would have a like term to combine, so we'd have to move the plus 1 to the other side by subtraction. So now we have y equals negative 4x plus 7. This now looks like the other functions we were working with. So, do you know the starting point of your graph? Yes, we know the starting point will come from this part of our equation, and that's telling you that the output has to be 7. So we have a point at 0, 7. That would be your y-intercept. Then, how are you going to find more points on your graph? What is your slope, your rate of change? Well, that will come from here, and notice how it's negative, so it means you're going to be going down 4 and to the right 1 unit. And we're going to repeat that till we run out of space, and we can see some of our sample points for our line. And again, we can take any value for x and substitute it in and get an output, so we know that it's continuous. Would this be considered a function? Yes, it would, because every input has one output. So function, yes. Well, What would be the domain? Well, again, as we look at the set of inputs, there are no restrictions, so that's going from negative infinity to positive infinity. What about the range? Are there any restrictions on your outputs? No, there is not, so that's going to repeat from your domain. So your range is from negative infinity to positive infinity. Do you have any locations where it crosses the x-axis? And we do. We can see it's happening here, but it's not at a grid point. So is there a way we could find where that happens? Well, we know for x-intercepts, the output has to be 0. So what's the input that goes with it? Well, if we take 0 and put it into our equation, whether it's the original or the one we simplified, we could solve for x and see what that value is. Well, if we put a 0 here, now we've got 0 equals negative 4x plus 7. We'd have to subtract 7 from each side, so we'd have negative 7 equals a negative 4x. How would you get x alone? We would have to undo the multiplication of negative 4, dividing each side by negative 4. A negative divided by negative is a positive, so here we know our input value has to be a positive 7/4. Now, is there anything that you notice about our graph with how it relates to the original equation? Well, we know the rate of change, the slope, was negative 4, and that appeared here in our equation. So we can still look in the same place to find our rate of change, the slope. Now, we had a starting point of 0, 7, and that's where it fell in this equation. But is there a starting point in the original equation that we could use? And if I look, I have some coordinates with an x and a y. So let's see. This says x minus 2 and this says y plus 1. Is there a location that we could use on our graph that might be related to that? Well, let's see. I'm going to look for 2's. So, and that was with the x. I'm going to look for x's of 2. So x of 2 was here, and notice how it's got a y of negative 1. So this point right here is at 2, negative 1. Well, how does that relate to your equation? Notice how it's the inverse of what you think it is, right? Here, x minus 2, you might think of that 2 as being negative, but really it's a positive. And here, you've got y plus 1. You might think that y is a positive, but really it's a negative. So here we're given a starting point on our graph and the slope. And so if we just plotted that starting point and used the slope, we would not have to do any of the multiplying out of the equation to put it into this slope-intercept form. We could have just plotted the point to negative 1 and did our slope from there, going down, forward to the right 1 repeatedly to get the points on the graph. And notice how it's the exact same result. All right, let's try this last one. Here we want to graph x minus 2y equals 14. Notice this is not like either of the two formats that we've seen so far, but we could manipulate this one to make it a y equals, similar to what we've had with the previous problems. So in order to make it a y equals, we would have to start undoing our equation. So that means we would have to subtract x from each side, and then divide every term by negative 2. That would give us y equals negative 7 plus 1/2 x. Now, what does this format of the equation tell us? We should be able to pick out that we have a starting point involving negative 7. What coordinates would go with that? Well, the starting points are all our y-intercepts, so we know our y-intercept is at 0, negative 7. How can we generate more points for our line? Well, we're going to find the rate of change, the slope. And we can see in our equation the rate of change, our slope is 1/2. That means we're going to be going up 1 unit and to the right 2 continually to get the points on our line. So we know that this is a continuous relation. Is it a function? Yes, it is. Every input has one output. What would be the domain? Well, we can see because it's continuous and not stopping because of the arrows on the end of our line, the domain would have to be from negative infinity to positive infinity. The same would have to be true for the range because it's never going to stop. That would go from negative infinity to positive infinity as well. The question is do we have an x-intercept? Looking at this part of the window of our graph, it appears that it does not. However, think about what's happening with your line. It's going to continue on in both directions. So looking to the right, we know it will eventually hit the x-axis. The question is, will that happen? To find that, we know that when it crosses the x-axis, the output is always 0. So if we put a 0 into our equation, simplified format or the original, and we solve for x, we'll have the x value needed for the coordinate. So I'm going to go back to the original equation and put in my output value is 0. Negative 2 times 0 is 0. So x and 0 equals 14, therefore x is 14. That is the x value for the coordinate of my x-intercept. So if I zoomed in my graph a little bit further to the right, I would see that it would be crossing at 14, 0. So a couple of things to remember when you're graphing your linear equations. There are two formats that you can graph from. One is called your slope-intercept form, and the other is your point-slope form. Slope-intercept form is commonly known as y equals mx plus b, where m represents your slope, your average rate of change, and b is the y value for the coordinate of your y-intercept. Finding those two things in this format makes graphing very quickly. Vertical lines, we know, only have an input value, so you'll see those written as x equals and whatever number the input is. A horizontal line has the same output value, so you're going to see those equations written as y equals an output number. We know that the vertical line has a slope that is undefined, and the horizontal line has a slope that is 0. The other way to write an equation for a line is your point-slope form. That is where you are inserting the coordinates into this standard form. Y minus y1 equals m times the quantity x minus x1. Y minus x minus is standard. M is the rate of change or slope, and the 1 point that you're given to start on the line, you take the x coordinate and you substitute that here. You take the y coordinate and substitute that there. If these were negative values, you know that if you subtract a negative, it's like adding a positive. So you'd want to simplify that and change your signs accordingly. But always take the x coordinate, put it into your expression, that's always a minus. Your y coordinate, always into your expression, which is a minus, and simplify if need be. Now it's your turn to practice. Based on the equations, can you graph your linear equations and identify key features of x-intercepts, y-intercepts, domain, and range?